Are you still solving your cross pieces one at a time? Would you like to get faster, but then C4 and advanced cross is just too intimidating of a concept to dive right into? Well, this video is just for you. Because today, we are going to help you get faster by building a hypothetical bridge between an absolute beginner cross to an advanced cross. So without further ado, let's get into it. Essentially, I broke down advanced cross to its constituent components, to its core elements, and simplified them for the beginner to be able to understand and implement right away. And what's the result? Adjacent theorem and opposite theorem. By understanding and applying these theorems, you would have already captured the essence of a full-fledged advanced cross just in a smaller, less intimidating package, and I promise you, by the end of the video, you will be one step closer to a professional speedcuber. Although I'm not one. So without further ado, let's get into it. So first, let's address what I like to call the first principle of adjacent theorem. It basically states that the order of solving adjacent pieces matter. When you see this case right here, many beginners will choose to randomly solve one of these cross pieces first. A slightly more experienced cuber, you will be able to see that the order of solving the pieces matter, such that if I solve my green first, I can also solve my red in just one move each. On the other hand, if you were to solve red first, the green will get messed up, and now you have to use a total of 4 moves to solve both pieces at the same time. Now let's talk about shifted adjacent theorem. Well, it basically goes like this. Shifted adjacent theorem states that if a centerpiece is on the left or right of another centerpiece, then their cross pieces can be solved in the same sequence. So let's look at our green cross piece right here and our red cross piece right here. As you can see, the green centerpiece is on the right side of the red centerpiece. We can translate that same sequence onto our cross pieces, in which, even though the green does not belong here, obviously, and my red does not belong right here, obviously, I can solve the green cross piece at the right side of my red cross piece, like this. And I know I can do that because when I refer to the color scheme of the center of the cubes, the green is in fact on the left side of the red. So no matter what side of the cube I am facing, even if green does not belong here, I know that if I solve green right here and red right here, I can shift the bottom layer to solve both simultaneously. Hence the name shifted adjacent theorem. And it's not just when the situations are like this. Even when you have to solve them completely opposite to where they belong, like this. Obviously, the green and the red do not belong here or here. But I will still solve them in this way before shifting the bottom layer to fix them both correctly. Now, there's actually something I like to address. In all the examples of adjacent theorem I have used before this, I used this specific situation in which my red is right here and my green is right here. Now, I don't want you to get a misconception that you should memorize this situation and that adjacent theorem can only be used when you get this specific situation. In truth, as long as you can solve the green adjacent to the red correctly, that is to the right of it, then it is possible to use adjacent theorem quite conveniently. For example, this case right here, which is actually just this case but shifted like downwards. This is actually even better because it saves moves, and we can set up adjacent theorem using just one move before, fixing. Our second case is right here, where my red is here and my green is right here. As you can see, it's just the default case we learned but shifted upwards. And also we can solve it quite easily using adjacent theorem, like so. And then solving both. And the last case would be this one right here, where the red is here and the green is here. Now I'd consider this to be the least intuitive out of these extra examples, but then you will notice that it's quite easy to solve the green at the right side of the red. Because in truth, while this is the default state that we learned, the state I just shown is just this piece being turned over here, in which it is one move to the bottom where it belongs, no matter if it's at the front or at the back. So, in a nutshell, what I'm trying to say is, adjacent theorem can also be very conveniently used if this cross piece right here, when we're solving it, adjacent to the red, is either here, 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 or here, which are the cases we have previously demonstrated. And there's one more thing I would like to talk about. It's sort of a mirror case. I guess right now we can call it this, that our white cross pieces, the whites facing to the left like so. But then what if we get a case like this? Still looking at the red and the green, now we can say that they're facing to the right. Now I'm sure this will be no challenge to you, since all my viewers are smart, that adjacent theorem can just be set up like so, using the exact same set of logic. It's just that they are facing a different direction now. It's still the same. Red to be solved at the left of green, because red center is at the left of green center. It's actually just either this, or I'll just do or this. They are one and the same, and I'm sure you will be able to see that. So now, what is opposite theorem? To explain it, I'll be using my blue and my green cross pieces. So opposite theorem states that the blue and the green cross piece can be solved opposite to one another because the blue centerpiece is always opposite to the green centerpiece and vice versa. Of course, this also applies for the red and the orange, but I'll be using my blue and green to make examples. So if you see a case like this, beginners will see this and do the best solution indeed, which is like this. But the challenge arises when beginners get a case like this, in which we are still looking at my green and my blue, and now suddenly they can't see the solution anymore. Well, going back to the exact same case, it can actually be solved in 3 moves. 1, 2, 3. As you can see, we have successfully solved the green and the blue piece simultaneously. And how did we do that? We applied the opposite theorem, in which if I can solve my green opposite to my blue, no matter what side of the cube I'm looking at and no matter what state I am in, we can solve them like this before shifting the bottom layer to solve both at the same time. It's quite intuitive that this isn't the only state in which an opposite theorem can be conveniently set up. If we get a case like this, mind you, we are still looking at the green and the blue, it's now actually easier to set up the opposite theorem. Solve the opposite, shift the bottom layer. And even if we get a case like this, still looking at the green and the blue, it's still really obvious that I can solve them opposite to each other and shift the bottom layer. And lastly, the least intuitive one is if you get a case like this, green, blue. But actually, it's also quite easy to solve the green and the blue opposite to each other. Just that instead of the pieces being like this, the blue was like this. Well, I think there's only one quote-unquote special case worth addressing, which is this one right here, still looking at the green and blue. So when both cross pieces have their white facing in the same direction, you can deduce that it is just one move away from being conveniently set up to do an opposite theorem, using an F move or an F prime move. And there's no need to memorize this. When you're trying to think of a cross solution, feel free to turn around a little bit. I'm sure you can easily notice that just with one move, you can solve these 2 pieces opposite to one another. Okay, so with that being said, all the theory I have finished teaching, and now it's time for some examples. Now, I'd like to apologize for my voice. I'm a little bit sick while recording this one clip, so my voice will be a little bit weird, but it's okay. So, for this, the first scramble is right here. Remember to do the scramble with white top and green front, which is facing you. If not, you won't get the same scenario. So for this example, it's quite a good opportunity for me to talk about how to apply adjacent theorems in real solves. Because look at this, my cross pieces are here, 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 and right here. So here we can quite conveniently apply adjacent theorem to solve the cross using quite few moves. So first thing you might notice is that the orange piece, I can solve it to the left of my blue cross piece. And just so conveniently, the color scheme is correct because my orange center is at the left of my blue center. So if you saw that, it'll already be a better solution than the previous one showed to solve these two like this according to adjacent theorem before shifting the bottom layer to solve both at the same time. And maybe that's not what you saw. Maybe you saw that the red can be conveniently solved at the right side of the blue cross piece like so, while the red center, as a matter of fact, is at the right side of the blue center. So it'll also be a good solution well compared to the beginner solution to solve the red right here according to adjacent theorem and fixing it with a shift. Now I want to get into a slightly more optimized solution based on the theorems taught, and hopefully after maybe a few weeks or maybe even a few days of applying these theorems in your cross solutions, you will be able to see such a solution. So essentially, I'm solving both the red and the orange, I mean the orange right here, and the red adjacent to the blue. You can look at this from multiple perspectives. You can say that, oh, I'm solving my orange adjacent to the blue, correct to the color scheme, and at the same time, before shifting it, solving my red right here. Therefore, making it also correct at the right side of the blue, just like the sequence of the colors on the centers right here. Well, if you want to look at it from another perspective, you can call it sort of an opposite theorem in which my orange is solved opposite to my red. In the end, we are combining adjacent theorem and opposite theorem to get a better solution, essentially solving 3 pieces at a time instead of 1 or 2. So now, I would like to teach the advanced cross solution just for educational purposes. So what I want to say is, the advanced cross solution, which is quote-unquote the best solution, well, at least the best that I can see, don't get into X crosses yet. So the best solution is solving all 4 cross pieces at the same time. That means that in my regular solution that I showed just now, the green will still be here, and the green will be quite a nuisance to solve. So what I want to do in the advanced cross solution is solve my green at its correct position. So what I will do is solve it to the back right here so that it can be opposite to my blue. And to do that, of course, I can't do that because it'll mess up my red. So what I'll do is I'll solve the red first. Now I can move this freely. And of course, I can't solve my orange first right now because it'll mess up the green. I'll fix my green first, like so. And then I'll solve the orange right here. And now as you can see, just with a shift, I have solved all 4 pieces of the cross. So what's the point I'm trying to make showing the best advanced cross solution? I'm trying to say that the leap between a completely beginner cross and an advanced cross is way less than you might imagine. It is quite intimidating of a concept, but if you break it down to just adjacent theorem and opposite theorem, you will be able to pick it up in no time. So with that being said, let us move on to our second example instead. Okay, on to the second scramble. So my cross pieces here, 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 and here. Once again, I recommend you to do this scramble for yourself and try to find a solution because this is honestly quite a good scramble. It's quite interesting. Okay, so the first thing I'll notice is that I can solve it using adjacent theorem, in which my blue is on the left side of my red, and so conveniently, my blue center is set up to be solved at the left side of my red center. My mistake, I meant blue cross piece and red cross piece. So I can just solve it like this, solve my blue right here, solve my red right here, and then solve it with a shift. And then the remaining two, I can deal with them, separately. Another thing you might see is the use of opposite theorem, in which the red and the orange will be used. It goes like this. Maybe you have noticed that if I solve my red here, according to opposite theorem, my orange can be solved right here. Well, opposite to it. It doesn't take too much notice that the orange piece just so happens to can be conveniently set up right here to be solved opposite to the red, just like so. And then you can just, shift it and solve it. So now let's move on to the second solution. We'll combine the opposite theorem and the adjacent theorem that we've pointed out to solve 3 pieces at a time. Okay, so the way we combine it is by solving the red opposite to the orange here and here separately, while solving the blue adjacent to the red to follow a color scheme of red, blue. So how we'll do it is a little bit more complicated. We'll have to solve the orange first, because if we were to solve, the blue first, it'll mess up the orange. And if we solve the red first, well, I'm sure you'll notice it'll mess up our blue right there. So what I'll do is move the orange here so that it can be solved opposite to the red, which I will solve here later. I'll solve that first. And now I want my red to be here. But then I notice that the blue can be solved right here. Then it will be correctly adjacent to both the orange and the red. So I'll solve my blue first, solve my red, and then shift the bottom layer to solve 3 pieces at a time. And then I can deal with this. So now let's talk about the advanced cross solution that I would do. It's actually quite similar, in which I'll move my orange right here. Now instead of holding the cube like this, I would prefer to hold it like this if I were to do this solution in real life. So I'll solve my orange at the back using a finger trick like so, such that I can set up my red right here opposite to it. First I'll solve the blue adjacent to the orange using the adjacent theorem. And next, instead of solving the red like this, that will cause the green to, be in a suboptimal state, what I'll do is I'll do a finger trick like this to push my green here, solve it, solve the red, and then I can shift across to solve it. And that is essentially the entirety of advanced cross. Then I can, continue my solution and solve the cube. From now on, how I want you to practice is that while you solve the cross, try your best to use the theorems that I taught to solve 2 or maybe even 3 cross pieces at a time instead of 1. And for the remaining cross pieces, just solve them 1 at a time as you usually would. The point of this is that over time, you will get 2 skills. Number 1, you will be more comfortable at solving shifted pieces. And number 2, you will develop a strong intuition on which pieces are adjacent or opposite to each other. And once you're familiar and consistent at said skills, I firmly believe you will be able to pick up advanced cross in no time. The journey to mastering advanced cross is a long one, full of experimentation and experience. I hope that this video has been of help in giving you some resources and lessons to bridge the gap between your current skill level and that of C4. To sum things up, I hope you enjoyed the video, and if you did, feel free to give me any feedback in the comments, because this is my first time doing an in-depth speedcubing tutorial. And if you are interested, feel free to subscribe.